If you remember the rules for a circuit, the sum of the voltage drops is going to be equal to 0 in any loop through a circuit. So that automatically should suggest to you that a group of resistors in series are going to divide the voltage. It has to be true. In fact, as we've discussed, in this circuit alone, this has to be true. Correct? Now, we also know that because they're in series, and we proved this using this same rule, that the equivalent resistance is equal to the sum of the resistors. Correct? Now, solving this circuit will show you what the voltage is across these resistors. We've done that. In fact, it shouldn't be too hard to do this without using numbers if we wished. So I could say the actual circuit looks something like this from the standpoint of the EMF, correct? And in fact, the current in that circuit, based on what we've already talked about, is going to be equal to this, right? That has to be the current in the circuit. Any question about that? All right. That suggests that V1 will have to be I R1. Is that true enough? I'm not doing anything here we haven't done, except this time there's just not a number there. And we did do this about a month ago. This is how we proved the equivalent resistance equals the sum of the resistors. Now, it's not much of a stretch now to go and look at what has to happen next if I want to see what... Now, it seems to me that tells me that V1 is going to be the total EMF times a ratio of R1 to R1 plus R2. Is this what you wanted? A way to divide the voltage out using the resistance only, because that's what it would be. If you wanted to see the ratio of V1 to V2, you could go one step further, right? If I do V2, well, V2's got to be the EMF times R2 over R1 plus R2. Still, nothing fresh here. I just have no numbers in it, right? So do you want something that you can memorize that'll give you the ratio of the two voltages? We'll divide those out. And I'll get V1 over V2 is equal to R1 over R2. Should you memorize this? No. This works fantastic if there's only two resistors and they happen to be in series. And that's the epitome of your entire circuit. You understand the limited case use there? But go ahead. It's a very limited use. You look up stuff on Google, you'll find all sorts of stuff like this. But you should be able to get there, right? Because it comes right back from Kirchhoff's laws. That's directly where it comes from. It has to be this way. Those ratios have to work out. If you just take a look at this equation, I just did the substituting, the same substituting as before. Right? It's going to indicate that these two voltages, which is what these are, this is V1 and V2, are going to be related by the resistance. The larger resistor is going to get more of the voltage. That's right there, isn't it? So it's there. Does it really simplify your work? I mean, if you want to do the math on it, so to speak. Let's look at, say, this circuit. So it's kind of messy, but that's the circuit that's at the front of the room right now, the one that you guys You guys got to play with it at the beginning of class if you were here on time and if you had a moment and there was not a crowd. So that probably means one of you got to plug it in and unplug it. There's two states of the circuit, the t equals 0 state and the steady state, and then there's the transitional time. Yesterday when I came back, and thank you one student for going in to talk to them about physics, appreciate one of you stood up. In the circuit, the short term is that there'll be no current passing through the resistors at t equals 0. But then the moment a voltage starts to develop across the capacitors, there's going to be current passing through the resistors, because now there's a voltage across them as well. And that will slowly build until the capacitors are fully charged. So the steady state of this circuit is that. That's the steady state. When the capacitors are fully charged, you just have two resistors in series. That's the steady state of the circuit. And yes, now it's a voltage divider. It was a voltage divider before. Two capacitors in series will also divide the voltage. Not the same way, because capacitors deal with voltage different than resistors do. Go ahead.
At time equals 0, would the circuit just look like two capacitors because the voltage just goes through the least resistance?
Technically, at time equals 0, it will be instantaneously a short circuit, because the capacitors act like zero resistance when they're uncharged at t equals 0. So for that instant, technically you could say there'd be infinite current, but there really wouldn't be. But the t equals 0 circuit is that. That's why nothing lights up. But that's not what's happening. And that goes to your question. Gabby says, well, she didn't understand the relationship here between the charging of the capacitors and the current in the circuit. That's difficult because you have to string together a couple of conversations. So I want to hand Gabby's question because it speaks to something we talked about a month ago, and that is, what is a capacitor? If you don't understand what a capacitor is, you're certainly not going to understand what these circuits are doing. So a capacitor, as defined by what we talked about a month ago, is any two conductors in space are capacitors. They may not have much capacitance, but any two conductors in space is a capacitance. In fact, we defined it based on that idea, that if I have any two pieces of metal in space, we will define capacitance as how much charge I could take from one and place on the other when I apply a voltage between them. That's a mathematical definition. If you want it better, here we'll put 3 of these little bars so we can make it a definition. But we're defining capacitance this way. And all it's suggesting is that if I put a potential difference here, and again, there's more here, and it speaks to your definitions. A potential difference exists because there's an electric field there. So when I place this potential difference there, I'm, in a sense, creating an electric field between the two pieces of metal and a conducting pathway through which charges could be moved. And quite simply, even if I don't want to do that, if I want to go back to chemistry, maybe you'll remember a little bit of that, opposites attract and likes repel. So the positive side of the battery is repelling positive charges away, and the negative charge of the battery is attracting positive charges. And we know it's the reverse of that because it's not actual positives that are moving, it is negatives that are moving. But let's just not even worry about that, because I'm not sure you're there. So when I connect this, a positive charge, whatever you want to call it, a +1, is sucked out of the piece of metal on this side, and through the magic of the battery, spit out on this side. That creates a negative charge on this side and a positive charge on that side. That's charged now. What's the total charge on the capacitor? We would say Q. But the truth is, I didn't create new charges. The battery didn't give me charge. That's never happened, and I've never suggested that. When we say we're talking about the charge on a capacitor, we are talking about how much charge has been moved from one plate to the other. That's a capacitor. So I will say, for all of you who are finding this hard and struggling, what part of that did you not write down and not have in your notes? Because that's just the basics of what I drew, the little potatoes. Remember? I remember drawing the potatoes and even commenting, now here's 2 potatoes. And then we spent 3 weeks refining that idea, because 2 potatoes shaped like 2 potato-shaped pieces of metal. So I crumple up 2 pieces of aluminum foil, throw a wire between them across the battery. Do you really think I'm going to move very much charge under those circumstances? We talked about what could we do to make this value bigger, which means what can we do to move more charges with the same voltage? So we spent weeks talking about different ways we could do that, starting with what is considered the most basic type of capacitor, a parallel plate capacitor. Because I indicated to you that if you want to ramp this up, the best way to do so is to find a way to maximize the electric field that you create from your applied potential difference. If you can maximize it, you could move more charges, because it comes right down to the fact that charges only move because you're pushing on them. An electric field pushes on charged particles. So I suggested we find ways to look at uniformity, things that we could control, things that we could measure. And one way to do that was to find shapes of our pieces of metal that created electric fields that we had already discussed. So one of the ones we talked about was the parallel plate. And we used this one specifically because we had taken a lot of time earlier in the year to talk about the shape of an electric field that is formed near a charged plate. So we knew about the uniformity of the electric field between the plates. Now we had to find a way to create that electric field, and the best way to do so was to put a potential difference between the plates, because that's going to pump charges. This is the same thing, right? Same picture now, but we know that there's a certain amount of uniformity in the field. Therefore, we could use rules that we had developed earlier to talk about how big the electric field is between these plates when charges begin to move. In fact, we came up with a structure of how we could figure out and predict what the capacitance would be for something shaped like this. And we found out that if we are careful and do our calculations correctly, that how much charge can be pushed ends up having repercussions based on the geometric shape of the plates. That if I want to have something that will allow more charges to move with the same voltage, one way to do so is to get the plates very close together and give them a large surface area. That's what that says there. But that still is directly related to our definition of capacitance. This is how you make one. This is what it does in the circuit. So when we say how much charge is on the capacitor, it's still the same number of charges. The charges were there already. All we did was move them from one plate to the next. So in this circuit, and I don't want to use this circuit because it's way complicated. 2 things, 3 things. Let's just do a simpler circuit that doesn't no branching, just one capacitor and one light bulb. And let's add a switch so we can at least discuss what happens at the t equals 0 and the t equals infinity moment. So I close the switch, and I have a capacitor of value C and a bulb of resistance R. And I apply an EMF of some value E. When I close the switch, does the bulb turn on immediately? We should know the answer to this. At t equals 0, does the bulb turn on immediately? No, I'm getting both yeses and nos, and a lot of people just sitting there. Want to ramp up the level of concern? Assign a couple of points to whether your decision is right or wrong. No problem with me for that, because you should have the answer. So let me be very clear. If the apparent resistance for the capacitor at t equals 0 is 0 because it's uncharged, then the only resistance in the circuit based on Kirchhoff's law will be the resistance of the bulb. But there's a complete pathway. So I am going to draw as much current as the bulb will want from the battery. 6-volt battery, 2-ohm resistor, I'm going to get 3 amps. Whatever Ohm's law tells me is what I'm going to get. In fact, I would bet that that'll be the maximum amount of current I'm going to get. And at that moment, I will have all the voltage across the bulb. Is it going to stay that way? I don't think so. Do you know? Do you know what will happen over time? Because you should. You should know that over time, I'm going to be taking electrons from one side of that capacitor and depositing them on the other. And so we're going to start to develop a positive side to the capacitor and a negative side to the capacitor. That capacitor is going to have a potential difference. And for an instant in time, there will be a potential difference across that capacitor, which will be based on how much charge is on the capacitor divided by its capacitance. You should know that. Now, it'll just be for an instant, because Q is going to change over time. But for that moment, for this instant, after time equals 0, there is a potential difference across the capacitor, which means there is less potential available to go across the resistor. It's a divider. But it's a divider where the dividing line is changing over time. So for a moment, we had full current. After that, not so much. So the voltage on the resistor drops, the voltage on the capacitor increases. Even if you want to just move some things around, right? The voltage across the capacitor, it means there's less voltage across the resistor. So with less voltage across the resistor, current's going to go down. Has to. Now, did I really just take charge from the battery and shove it in the capacitor? Is that what happened? No. Not at all. Now, over time, the capacitor will eventually reach what is going to be its maximum charge. Over time. And over time, we will get the full capacitance, we'll get the full charge on the capacitor when the voltage across the capacitor is equal to the EMF. When that happens, there's no voltage across the resistor. So there'll be no current in the circuit. That's what's happening. And we know more than that. Because we know, the charge as a function of time is going to be equal to some Q max, which has got to be this. That's Q max for this circuit, an RC circuit. We proved that in class. Well, I did. I don't know what you did. This is how long it's going to take, which suggests infinity, but we know better. Infinity isn't that long. For these circuits, apparently it's a couple of seconds. Pretty good. Now, I suspect, with your advanced skills and lack of hubris, that you guys could figure out how much current is passing through this circuit. All right? Take a minute. We didn't do this in class. I asked you to do it at home, which I'm sure you ran out and did. But you should have I as a function of t. It could be in your notes because you actually did what I asked you. It's also somewhere in your homework, I'm sure. But maybe you didn't. We did this just the other day for a discharge circuit, so I'm not asking too much. A lot of donuts. But let's start with what I think is the obvious. I'm going to take the derivative of both sides of charge. So dq dt and d dt of EC to the 1 minus e to the negative t over RC. EC is a constant. I can just bring it out front. And now I can distribute the derivative So d dt of 1 minus d dt e to the negative t over rc. All good? The derivative of 1 is 0. So I can just get rid of that. Right? Derivative of 1 is 0. But when I take the derivative of e to the negative t over rc, I will have to use the chain rule. And since this is the exact same set of steps from yesterday, you understand my frustration. But I will take the derivative of e to the negative t over rc by first saying that the derivative of that is e to the negative t over rc. And now I have to take the derivative of negative 1 over rc. I'm sorry, negative t over rc. And just like yesterday, the derivative of that is just negative 1 over rc, right? Because it becomes t to the 0 power. So, EC, negative e to the negative t over rc, and negative 1 over rc. Alrighty? The negatives cancel, the c's cancel, and I will get e over r, e, so we have t over rc. This has got to be the current as a function of time. It's important to understand that this is different than yesterday. There's a negative sign yesterday. Negative sign is about the direction, about the flow of the charged particles. It's not direction, because current isn't a vector. But the results are the same. I get a decaying exponential, which means in this case the current goes away over time. Are we surprised by that? No, that's how we determined that the capacitor acts like a resistor. That's how we determined it. That's where that came from. And yeah, I'd hoped you'd done that. Now, Gabby's still struggling with why this is different than what we did yesterday. Well, yesterday we were dealing with a different circuit altogether. Yesterday we were trying to understand, I believe, something out of your homework that looked more like this. Is this more akin to what we were talking about yesterday? It was built right there at the front of the room. We talked about this circuit specifically. And we said we close the switch and we let the whole thing charge up. Tried to talk about the difference between the steady state condition and the time equals 0 condition. In this particular circuit, in the time equals 0 position, when you close the switch, do both bulbs light up, or does one bulb light up, or do no bulbs light up? Which one, R1 or R2? That's right. I first close the switch, R1 lights up because the capacitance is uncharged, acts like 0 resistance, and shorts out the other bulb. So only R1 lights up. Does that last very long? No. Immediately, the capacitor is going to begin to charge. And again, I'm answering this question because I think, although it was brought to me by one student, the group of students that sat there while I was explaining this before school clearly suggested that this is a widespread problem. But nothing comes out of the battery in a sense like it's just pushing things out there. It is moving stuff that's already there. That's what the battery's doing. So for every charge that comes out of the battery, a charge went into the battery. So what happened the moment this switch was closed was, current passed through the resistor. Why? Because a charge exited the battery and charge came into the battery. And when it did that, it was pulling the charge off of one side of this capacitor and depositing a charge on the other side of that capacitor. So that instantaneously an electron got taken away from one plate and put on the other. The moment that happened, there was a potential difference across the capacitor. How do I know? Because I have an equation that tells me More importantly, it's defined this way. So that's what happened. A voltage immediately developed across the capacitor. The moment a voltage developed across the capacitor, there's a voltage on both sides of our parallel circuit. So now I have a voltage across bulb number 2. So bulb number 2 is going to begin to pass some current. Over time, what happens? The capacitor becomes fully charged. When the capacitor becomes fully charged, it acts as though it has infinite resistance. Actually, it doesn't act. It always had infinite resistance. It's just that now, because it's fully charged, no more charges can be placed on the capacitor. So its infinite resistance shows up now, because it can't hold any more charges. It can't take any more charge from one plate and deposit it on the other. Yep?
If it takes the path of least resistance, why does the second resistor begin to light up before the capacitor is fully charged?
Maybe you misinterpreted the way I should have said that. Or maybe I should have said it different. But Kirchhoff's law states that when current moves to a junction, the current's going to split up. And some current's going to go through one junction, some current's going to go through another. The amount of charge that passes through either junction will be dependent on how much resistance is there. So the side with,
Either way, it's just
well, unless one side is 0. If one side is 0, then all of the resistance will go that way. Mary, when you were looking up voltage dividers, did you look up current dividers too? Do you think there's probably something similar? Probably. But I don't know that we have to look it up. I think we can just look at a parallel circuit and see how the current will divide itself up if you have two resistors that are in parallel. You could do that right now and come up with a relationship between the currents. I bet there is a similar comparison between I1 and I2 in a parallel circuit. In fact, take a minute. I'll give you, I got time? 3 minutes to do what we just did at the very beginning of class. But this time, I want you to look at the current as it goes through both. And while you're doing that, because I want you to take a minute, I'm going to refine this because I want to go back to yesterday. I want desperately for everybody to understand. I don't like the fact that I've missed the mark, and it's hurting my feelings that I thought I'd hit the mark here, but obviously I missed it a lot, and I want you to understand. So don't take a, if you don't understand what I'm asking you to do, I'm saying take a simple, single, parallel circuit. As simple as it can be. And see how the current divides itself up. You're producing a current divider. Now, while you're working, because you're smart people, path of least resistance should rear its ugly head here. It should. So, and it will. I think you're going to see a relationship in which whatever is the larger resistor, it will have less current. You should see that. And everyone has a smaller resistance should have more current. You should see that. Does anybody need help doing this? So I can pick on anybody? You will tell me about it? Because I don't want to pick on you if you don't have the right answer. You know, I actually don't like that. All right, so you clearly are having an issue because you would be laughing at me, and you're not. Mary's voltage divider was V1 over V2 equaled R1 over R2. That's what the result was. Don't you have here I1 equals EMF over R1? And I2 equals EMF over R2. It's the same EMF on both. So if you just wanted the ratio of I1 to I2, you don't have to do anything else. It's right there. Just divide. So for the ratio, I1 over I2 is equal to R2 over R1. Does that show you what you think it would do? Does it show you that one side gets more of the current than the other? Does it show you that it's the inverse? That in this case, the larger resistance gets less of the current? I mean, do you see it there? If you don't, just solve for I1. And we get R2 over R1 times I2. If R1 is bigger than R2, then I1 is smaller than I2. What's this in the extreme? Well, when one of the resistors is 0. Right? If that R2 is the capacitor, and it has 0 resistance at time 0, doesn't that mean the current through R1 will be 0? Path of least resistance in the extreme. Does that make sense now? Now you could put this in terms of the equivalent resistance, but the voltage divider thing he showed was not comparing to the total, it was comparing to each other, and that's what that was. Now I still want to get back to actually answering Gabby's question because I think it's valid. This is the circuit we had yesterday, right? And I said we were talking about what happens when we cut the power. So if we let this circuit get to full charge, and then we pull the switch, do both bulbs instantly go out? Do you remember doing this yesterday? We can do it right here. The change in this circuit is to immediately take away all of this. And this became the new time equals 0 moment. Right? This became the new time equals 0 moment. Now, at this moment, the difference is the capacitor was charged. It had whatever the charge was across the resistor. I don't know what that was. We didn't work it out. Probably could use the voltage divider to figure it out, or Kirchhoff's rules, or whatever we want. And it is true. You could use that voltage divider thing that we just proved a minute ago to figure out what the voltage is right there, because it has to be based on the fact that the two resistors were in series. Kirchhoff's laws still have to work that way. But now that I have that, what's happening? Why is this bulb still lit up? The battery's no longer there. What's happening? What does that mean? Because that's the problem. Discharging, apparently, I didn't communicate that to you guys, and we need to have that communicated. There's certainly energy in the capacitor, right? We know that, or the bulb wouldn't light up. The bulb lights up because current is passing through it. So here's the critical things that I clearly didn't articulate. And it's probably just me. I think I'm a bad teacher. Current is the flow of charged particles. The brightness of a bulb is based on power. So if we talk about power, it lights up if there's current passing through the bulb. I could choose different relationships here, but I chose the one that has current in it on purpose because we want to know if there's current passing through the bulb. And we want to know what is current. It's the flow of charged particles. That's the definition. The flow of charged particles. So the bulb is lit. That means particles must be going through it. Now, the whole reason charges can move is because there's a complete pathway. There has to be a completed pathway. In this case, I had a capacitor where a bunch of electrons had been taken from one plate and placed on the other. That had built up over time because of the applied EMF. The moment I took that out, that resistor, that battery, they were gone. The only completed pathway is this pathway. And because this is the only complete pathway, there is a way for the electrons to go back, right? They're being attracted to that. This, right here, all of this, just this plate, let's look at just this plate, is filled with electrons. They're all repelling each other, right? They're pushing each other away. We had been applying a battery which kept them forced in there. And now that battery's gone. And there's a way for them to go from one plate to the other. So that's what's happening. The electrons are moving through the circuit, going from one plate back around to the other. That bulb will be lit until the plates no longer have a difference of charge. That means that it will continue to happen until the voltage across the capacitor is zero, until it's completely uncharged. But the charge isn't going anywhere. The charges were already there. They were just separated. That's the thing about a capacitor. Nothing that's coming out of that battery but energy. The battery moves the charges that are already there. That's all the battery does. In this case, the capacitor is moving the charges that are already there.